Have you ever just stopped and wondered if there are more dimensions out there than the three we can see? Well, today, we're diving into that exact idea and exploring how the answer completely changed physics forever. We are talking about the four-dimensional universe. So, when we hear the fourth dimension, our minds kind of leap to science fiction, right? But what are we actually talking about? Is it some other place? Is it a direction? How in the world can you even begin to visualize something that, by definition, exists outside of our three-dimensional experience? Okay, so the classic way to wrap your head around this starts with an analogy. Take a look at that first image, a simple 2D square. Now, to get a 3D cube, what do? You pull that square up into a new third dimension, perpendicular to the first two. Pretty straightforward. So, logically, to get a 4D hypercube, also called a tesseract, you do the same thing again. You pull the entire 3D cube into a new fourth dimension, at a right angle to all three of the others. Now, our brains literally can't picture that, but what you're seeing here is its shadow, its projection into our 3D space. So, long before physics gave us a solid answer, this idea of a fourth spatial dimension was this amazing playground for mathematicians and artists. It was a way to imagine a reality beyond our own, a way of, expanding perception itself. And this idea just took off, inspiring so much incredible work. You had cubist painters like Picasso trying to show objects from all sides at once, as if they were seeing through a fourth dimension. The famous artist Salvador Dali actually painted Christ on the unfolded net of a hypercube, and even modern architecture, like the La Grande Arc in Paris, is designed to look like a 4D object casting its shadow into our world. It's wild. So for a long, long time, that was the story. The fourth dimension was just another direction of space, like up-down, left-right, forward-back. A fascinating geometric puzzle for sure. But then, physics discovered something completely different. Something far, far more real. And this is where our whole understanding does a complete 180. Physics found the true fourth dimension, and it wasn't some abstract, unreachable direction in space. No. It was something we experience every single moment of our lives, time itself. This incredibly powerful statement came from Hermann Minkowski back in 1908. He was studying Einstein's brand new theory of special relativity, and he had this stunning realization. He basically declared that space and time weren't separate things. They weren't just the stage for the universe to play out on. They were actually woven together, threads of a single unified fabric. And that unified fabric is what we now call spacetime. In this model, every event that happens in the universe doesn't just have a location in space, an X, Y, and Z coordinate. It also has a location in time, a T coordinate. It's all one single four-dimensional address. But here's the catch, and it's a huge one. You can't just treat time like it's another spatial dimension. Space-time has its own unique geometry, its own rulebook, and a completely different way of measuring things like distance. Think about it. In regular 3D space, we find the distance between 2 points using the Pythagorean theorem. You add everything up. But in space-time, the rules are totally different. Look closely at that formula on the right. Notice how the time part is treated differently from the space parts. That crucial minus sign, that is not a typo. It's the mathematical signature of time itself, and it changes everything about the geometry of our universe. This special 4D distance is called the space-time interval, and it has a kind of superpower. It's invariant. That means it's a value that never ever changes. You and I, no matter how fast we're moving relative to each other, will always measure the exact same space-time interval between two events. We might argue about how much time passed or how far apart things were, but we will always agree on this one fundamental number. It's the universe's bedrock of reality. And this new geometry has huge implications for cause and effect. If the interval between two events is time-like, it means there's enough time for one to affect the other. They're causally connected. But if it's space-like, they're simply too far apart in space for even a beam of light to get from one to the other. You can't influence it, and it can't influence you. It's the universe's ultimate speed limit, baked right into the fabric of space-time itself. So how do physicists actually work in this strange new 4D world? Well, they needed a new mathematical tool, a new language that treats space and time as a single thing. And that tool is called the 4-vector. A 4-vector is actually way simpler than it sounds. You just take a normal 3D vector, like your position in space, and you bolt on a fourth component for time. That's it. This new object, now called a four-position, pinpoints a single event, a single moment, in the four-dimensional block of space-time. And this is where the real magic happens. Things that we always thought were totally separate in our 3D world are suddenly revealed to be unified in 4D. Take momentum. Its four-vector cousin, the four-momentum, doesn't just describe momentum, its time component is energy. All of a sudden, energy and momentum are just two different sides of the very same four-dimensional coin. Now, this unification, it's not just a neat mathematical trick to make equations look prettier. It's a profound shift in how we understand what's fundamentally real in our universe. Which, of course, leads us to the big question. Why? Why go through all this trouble? Why combine space and time and invent these four vectors? What do we actually gain from it all? The answer is surprisingly simple. We gain truth. The whole point is to find the invariants, the quantities that don't change no matter who's looking or how fast they're moving. In our everyday 3D world, measurements of length, time, even energy can all change depending on your motion. But in the 4D picture of spacetime, we can finally pin down the things that are truly absolute. So what are these universal truths? Well, we've already met the spacetime interval. Another one is a particle's rest mass, its true, unchanging mass. But the most incredible truth comes when you calculate the length of that four-momentum vector. When you do the math, what pops out is e squared equals pc squared plus m naught c squared squared. And for a particle just sitting still, that simplifies down to something you'll definitely recognize. E equals mc squared. That's right, the most famous equation in all of physics is a direct consequence of the four-dimensional geometry of our universe. So, here's the crucial takeaway. This four-dimensional perspective doesn't actually make physics more complicated, it makes it simpler. The fundamental laws become more elegant and, most importantly, they become universal. They look exactly the same to every observer, which is exactly what a law of nature is supposed to do. And we can end right where we started, with Minkowski himself. He always made sure to stress that this wasn't some fantasy he cooked up. These ideas came directly from the hard data of physical experiments. They are radical, he said, because reality itself was more radical than anyone had ever dared to imagine. This whole journey, from an artist's dream of a hypercube all the way to the deep structure of physical law, was powered by one thing: a change in perspective. It really makes you wonder, doesn't it? What other fundamental truths about our universe are just sitting there waiting to be found, if only we can figure out the right way to look?